All right, we're going to continue with this stoichiometry problem here. And in stoichiometry, we need the balanced chemical equation, so let's go ahead and balance this C8H18 liquid. We're burning this, so it's going to be plus O2 yields CO2 plus H2O. H2O is a liquid, CO2 is a gas, O2 is a gas. And so I have 8 carbons here, that means I need 8 CO2s, and then 18 hydrogens, which means I need 9 water. That's going to fix the amount of oxygens on the right. So it's going to be 16 plus 9, which is 25 oxygens. And so over here, I need N times 2 is equal to 25. So N times 2 is equal to 25. N is what? N is going to be 25 taus. Sometimes we use fractions. We use fractions because, take a look at this number here. I'm going to get this much energy for how much? Octane. For 1 mole. If I had 2 moles of octane, I would get double the energy. And so oftentimes we use fractions because of the energy. Now, is the energy a product or a reactant here? It's actually a product because the negative tells us energy is released. And so it's going to be plus 5471 kilojoules of energy burned. Okay, this is if I keep the fraction. If I get rid of the fraction, I have to multiply everything by 2. And fractions are, sometimes they're a hassle in stoichiometry, but sometimes they're not. In this case, I'm not dealing with O2, so I just want to know what mass of liquid octane. So I just need to relate this to this. And so I have a choice. I could double everything or just leave it. I'll just leave it. Okay, if we lose the negative sign, then we've lost something. You know, if somebody says $10, I went to the bank, $10. And you think, you went to the bank, $10. What did you do? Did you deposit or did you withdraw? $10, You don't know if they got a $10 bill or they deposited a $10 bill. And so this is why we need the sign. But if we lose the sign, we lose that information. Here, we lost the sign, but we retained the information, right? Because we see what side the equation's on. And so let me show you what I mean by losing a little bit of information. We've seen this problem, and this problem happens in math. You know, what's the square root of 4? The square root of 4 is, couldn't it be negative 2? Yeah, plus or minus 2. It could be negative. Well, tell me, was it negative or was it positive? You don't know because you've lost the information. That happens in math. And so to prevent loss of information, we verbally state something. And so this is the way we do it. Actually, this problem, we don't even really need much because we have 9.05 times 10 to the 4 kilojoules of heat. And then there are 2 ways of doing this. One way of doing this is we could say that there's minus 5,471 kilojoules of heat for every mole of C8H18. And then, well, what does it weigh? 8 carbons is 8 times 1201. 18 hydrogens, well, I can do that. I had 18. So 80 80 plus 16 is 9608. 9608. So add these two together. That's 16 to 14. 114.26. So a mole of this weighs 114.26 grams of C8H18 per mole. C8H18. So when I calculate this, well, what do I get? If I just use the conversion factor as written. If I use the conversion factor as written, I'm going to get 9.05 times 10 to the 4th. Divided by negative 5471 times positive 114.26. And so I'm going to get negative 1,890.0 grams of octane. In other words, it's probably easier in kilograms. This would be negative, I'm allowed 3, so I'd go negative 1.89 kilograms of octane. Okay, can you weigh out negative 1 kilogram of octane for me? No. Is there such thing as negative 1 kilogram of octane? There's no such thing as that. And so what do I do about the negative sign? Because math tells me I better have the negative sign. I can't get rid of it, right? Negative times the positive is going to give me a negative. And so what do I do? Well, this is the fix that we're going to do. You know, we don't want to lose. The negative tells us the direction, you know, of what happened. And so if we're going to lose that negative, then we're going to add a word. You know, we're going to add a word that... So we don't want to lose, that's called phase information. This happens in science. Because negative or positive makes a difference. And so what we'll do is we'll rewrite this. For every mole of octane, C8H18, I'm going to produce positive 5,471 kilojoules produced. So the produce just tells me it's a product. And I would take it as a loss. The reaction lost that times 114.26 grams per mole of octane. Oct is 8 carbons. And then we'll just convert it to kilograms. A kilogram is 1,000 grams. And so what we get is I need to burn a positive 1.89 kilograms of octane required. Let's see what the book did. You see the book just went ahead and did the positive, but when they do the positive like this, you're losing the direction, whether it's a loss or a gain. And so to prevent the loss of direction, in other words, what was it? If it's a loss, what do we call it? Exothermic or endothermic if we lose energy? The reaction loses energy. It's exothermic. And so if the reaction loses energy, well, energy is neither created nor destroyed, so everything surrounding the reaction is going to gain energy. Well, anyway, we lost that phase, but they didn't retain the phase information. You know, if the square root of 4 was negative 2, then we could say it's negative 2. Negative 2 times negative 2. Then we retained that. And so we know if it came from negative 2. In science, it's important to know, did it come from negative 2 or did it come from positive Well, that's the end of the PowerPoints there for chapter 10. But anyway, stoichiometry is a big topic in chemistry. So let's take a look at some stoichiometry problems from the book, get an idea. So when we look at 10.1, it's just mole ratios, 4 to 5 to 4 to 6 mole ratios there. So it's just mole to mole conversions here, 10.1. So look at those problems, they're all mole to mole conversions. In section 10.2, we kick it up a notch. We go grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. All these problems are the same. It's a gram to mole, mole to gram conversion. And so we could look at some examples here. Number 9. The explosion of nitroglycerin is described by the equation. This is the formula for nitroglycerin. This is decomposition. Is this a decomposition redox? Decomposition acid base? What is that? Decomposition metathesis? What is that? Immediately I can tell that this is redox. This is decomposition redox because I have elements over here, I have compounds over here. And so we're going element compounds. Well, we've got to change the charge. Elements of 0 charge. So how many grams of carbon dioxide are produced by the explosion of 21.0 grams of nitroglycerin? So we go from grams of A to moles of A here, to moles of B, which is CO2, to grams of B, CO2. So it's just a gram to mole, mole to gram conversion. So that's a representative example. Boy, here, number 11, soaps. We look at this. What kind of reaction does this look like? Although it's hard to see it here, this is actually a metathesis reaction. So number 13, one way to make sodium thiosulfate, which is used as the antidote to cyanide poisoning, is described by the equation. What does this look like? Some reactions are a combination of things. Yeah, this looks like a combination, kind of a metathesis plus acid base. This is a Lewis acid base. None of the oxidation states, well, maybe they do change. It could be some redox in there. We've got to look at the oxidation states carefully to see if there was any change in the oxidation states. And so there could be a mix of metathesis, redox, and acid base, that kind of thing. And so this is the way we understand a lot of these reactions. But all these are gram to mole, mole to mole, mole to gram conversions, all of them. And so a lot of practice there. If we go to 10.3, it's percent yield. Percent yield, we calculate the theoretical yield and then figure out the percent yield here. So here's the example. I calculate the percentage yield in the photosynthesis reaction by which carbon dioxide is converted to sugar. If 7.03 grams of carbon dioxide yields 3.92 grams of sugar, this is glucose C6H12O6. The equation is, all right, and so what we do is we calculate the theoretical yield. 7.03 grams of carbon dioxide in theory should yield how much sugar? Well, in reality we only got 3.92. we do the actual or the theoretical. So we got a number of problems like that. Theoretical yield is dictated by the limiting reagent. And so here they try to keep things simple by not introducing the whole concept of limiting reagent just yet. Here we do it, if we kind of have an idea of what the yield is, the percent yield is, then we can compensate for it. So this reaction has quite a bit of loss, about 30.9% loss. This reaction is a little better, but still it's 19.8% loss. So we can compensate for the loss that we expect, like we did earlier. And then we have limiting reactants. Here's some conceptual problems on limiting reactants. Just to get an idea of it. Here is the reaction of zinc with hydrochloric acid. Hydrochloric acid is CCS. Zinc is the metal down here. This reaction's gone to completion. When zinc reacts with hydrochloric acid, we form hydrogen gas. So this balloon is filled with hydrogen gas here. Which one is the excess reagent here? Which one's the limiting reagent? The zinc is the limiting reagent. We have zinc left over. That means this must be water. It's gone flat. There's no more hydrochloric acid in this water. It's just water now. Right? And so the hydrochloric acid's reacted. Actually, this was salt. The salt is zinc chloride in the water. Over here, this balloon's filled to the max. Actually, they should have made this balloon bigger, because do you see any zinc left? All the zinc's reacted. In fact, this is supposed to represent stoichiometric. This is supposed to represent stoichiometric. And this is supposed to represent excess hydrochloric acid. There's no more zinc, therefore it's a balloon, even though we have plenty of hydrochloric acid left. And so that's what this one is trying to show. And then we have limiting reactants here. Figure out the limiting reactant. We have two methods. I like the smaller amount method. And so all these limiting reactants, you're given the ingredients. Let's look at this one. Carbon dioxide can be removed by air by the reaction with potassium hydroxide. So CO2 reacts with potassium hydroxide to form potassium carbonate and water. What kind of reaction is this? It doesn't look like metathesis. Kind of looks like redox, but it isn't. It is acid-base. You're correct. This is a Lewis acid base. CO2 is a good Lewis acid. Well, anyway, in this we can remove CO2 from air. And so here they give us the ingredients. 15.6 grams of carbon dioxide, so that's ingredient 1. Mixed with 43.0 grams of potassium hydroxide, that's ingredient 2. So if we're given the ingredients, then we've got to figure out, do we have enough of each ingredient to react? So all these problems in this section, you're given the ingredients, the amounts of ingredients, and then we've got to figure out which one we don't have enough of, basically. It is possible, it could be a trick question, it's stoichiometric, we call stoichiometric. In the next section here, 10-7, we looked at energy, and these are just energy unit conversions here. So it's just one step. Dimensional analysis. Then we have thermochemical equations. For example, energy is transferred from sunlight in the photosynthesis reaction, in which carbon dioxide and water vapor combine to produce sugar, C6H12O6 glucose, and release oxygen. The amount of energy is 2.82 times 10 to the third kilojoules per mole of sugar formed. So we can just write out the equation and then figure out the delta H, where it goes, which side it goes on. So that's writing out the two equations, whether it's endothermic or exothermic. So you can read through all these problems and see what it looks like. Then we have stoichiometry. Here, energy is a reactant. Actually, this is it. This is the decomposition of limestone to form calcium oxide. And this is Lewis acid base decomposition. So, and this is a little different. What quantity of energy in kilojoules is required to decompose? So if I had 5.80 grams or kilograms of limestone, how much energy is required? Well, I know for every mole I need 178 kilojoules, so I can figure it out. I go grams to moles, moles to energy. All right. Well, anyway. So these are just the thermochemical problems like we did. Then we have some general, vocab here. True or false? Some additional stoichiometry problems. Nitrogen is very inert, and so here's an interesting reaction. It says one of the few ways of fixing nitrogen. Fixing nitrogen is to get nitrogen into a compound, so to go from an element to a compound, either by oxidizing it or reducing it. That is making a nitrogen compound from the elemental nitrogen in the atmosphere by the reaction. Sodium carbonate plus carbon plus nitrogen yields sodium cyanide plus carbon monoxide. Sodium cyanide very poisonous, carbon monoxide very poisonous. This looks like a very unpleasant reaction. It's an interesting reaction. This is a redox reaction, by the way. How about this reaction? Emergency oxygen mass contain potassium superoxide. Superoxide is not one I asked you to memorize. Superoxide is O2 with a -1 charge. O2 with a -2 charge is called peroxide. It's a little different than peroxide. And so here we take potassium superoxide, KO2 solid, and if you exhale CO2 into the CO2 reacts with the potassium superoxide solid and generates potassium carbonate plus O2. It's a redox reaction. So if the mass contains 125 grams of potassium superoxide, how many grams of oxygen can be produced? This is a stoichiometry. It'll be gram to mole, gram to mole, mole to gram conversion. Baking cakes and pastries. Actually, we looked at 74, didn't we? A laboratory test of 12.8 grams of aluminum ore yields 1.68 grams of aluminum. So in other words, they're extracting the aluminum from the aluminum ore. And so they only got 1.68 grams of pure aluminum from 12.8 grams of this mixture. This is a mixture here, a mixture problem. If the aluminum compound in the ore is Al2O3 and it is converted to the pure metal by, actually I don't like this problem that much, but by the reaction, what is the percentage of Al2O3 in the ore? Then 76, how much energy is required to decompose 1.42 grams of KClO3? If you look at the advanced problems, in a lot of the advanced problems we have mixtures. So for example, a phosphate rock quarry yields rock that is 79.4% calcium phosphate. The raw material used in preparing this, a fertilizer known as superphosphate. The rock is made to react with sulfuric acid according to the equation. If you look at that, that looks kind of like a metathesis, but this is a combined metathesis with some bronzite acid base. What is the smallest possible mass of rock in kilograms that must be processed to yield 0.500 tons of fertilizer? So this we got to use this. If we want 0.500 tons of fertilizer, which is this, then we go from mass of fertilizer to moles of fertilizer here. And then from moles of fertilizer to moles of pure calcium phosphate. And then from moles of pure calcium phosphate to, is that a mass percentage or a mole percentage? Is that mass percentage or mole percentage? What do you think? So we have some time. Let's do this one here as a quiz. We're going to do number 77 as a quiz. So. Okay, you know how many pounds are in a ton? 2,000 pounds in a ton. And there's 453.6 grams per pound. So those would be given. You wouldn't have to memorize that. So 1 ton is equal to 2,000 pounds. There's also something called a metric ton. Maybe this is it. And then there are 453.6 grams in a pound. We're going to have 2 problems, this one and then another one.